Hello, everyone. If you've tuned in for Woods Hole Oceanographic Institution's Ocean Encounters presentation on volcanoes, you're in the right place. Joining us tonight are marine geologist Molly Anderson, experimental geologist Emmanuel Codillo, and geochemist and geologist Forrest Horton. Stay with us. Hi, everybody. In just a few minutes, we'll get started with Woods Hole Oceanographic Institution's Ocean Encounters presentation, Volcanoes, how fiery forces from deep inside the planet shape our world. We've still got a lot of people joining us, so thank you for your patience. Hello, you've joined Volcanoes, a Woods Hole Oceanographic Institution Ocean Encounters presentation. We have a lot of people joining us tonight, so please bear with us. We'll get started very shortly. And now, please take a moment to read WHOI's land acknowledgement.
The ocean covers 70% of the globe. It gives us oxygen and food and millions of jobs. It brings joy and shapes our climate and weather. The ocean is life, and it belongs to everyone. Woods Hole Oceanographic Institution is the world's independent leader in ocean discovery, exploration, and education, working to understand and sustain one of humanity's most precious common resources. Join us today for our ocean, our planet, and our future.
Welcome to Ocean Encounters, a virtual series from Woods Hole Oceanographic Institution, or WHOI, as we like to call it for short. Tonight's event is Volcanoes, How Fiery Forces from Deep Inside the Planet Shape Our World. My name's Veronique Lacapra, and I'm the host of Ocean Encounters. We are now in our 6th season, and I'm happy to share that our series has once again been named an endorsed activity of the UN Decade of Ocean Science for Sustainable Development. I'd also like to thank our sponsors. WHOI's Ocean Encounters events are made possible in part by the Avatar Alliance Foundation and Dalio Philanthropies. Thank you to them. Thank you also to any WHOI members who are joining us tonight. You are the heroes at the heart of our efforts. Before I introduce our speakers, I want to let our Zoom audience know they can participate in tonight's live conversation. If you have a question for one of our panelists, please use the Q&A button on your Zoom screen and type your question in the little window that pops up. You might be more familiar with the chat function in Zoom, but please ask your questions using the Q&A button instead. We often get hundreds of questions, so I apologize if we don't get to yours while we're live. You can ask questions anytime, starting now. I also want to let you know that we are recording this event, and that recording will be made available on the whoi.edu website. We had more than 1,600 people pre-register to join us tonight, so you are in very good company. We also have viewers joining us right now on Facebook and on YouTube. Thank you, and welcome to everyone. Let's get started. Volcanoes make headlines when they erupt, but most of Earth's volcanic activity happens far from view, on the seafloor, thousands of feet below the ocean's surface. Tonight, we're going to hear a lot more about volcanoes, both those at the bottom of the ocean and on land, and we'll find out what we're learning from them and how they impact our ocean planet. Here to tell us more are 3 geologists. They are experimental petrologist Emmanuel Codillo, igneous petrologist and geochemist Molly Anderson, and geochemist and high-temperature petrologist Forrest Horton. Don't worry, we'll dig into what all those terms mean a bit later on in tonight's program, but first, some quick introductions. Emmanuel is a postdoctoral fellow at the Carnegie Institution for Science. He's a familiar face to us at WHOI, though. This is where he got his PhD in the MIT WHOI Joint Program. Molly is a National Science Foundation postdoctoral fellow in WHOI's Department of Marine Chemistry and Geochemistry. Forrest is also here at WHOI. He's an associate scientist in our Department of Geology and Geophysics. Welcome, everybody. Molly, I want to start with you. When I picture a volcano, I imagine one erupting on land and with big lava flows and smoke and gases like that. But what do volcanoes on the seafloor actually look like? How big are they and what are they doing down there?
Yeah, so most volcanoes on Earth are actually in our oceans. They range pretty drastically in shape and size. Some of them are small, they're round cones that form from like a single eruption. Some are these massive, broad volcanoes that form from many eruptions that occur over millions of years. One example of that would be the Hawaiian island volcanoes. Most volcanism on the seafloor actually occurs through long interconnected rifts that span almost the entire length of the ocean basins, and these are called mid-ocean ridges. Most eruptions on the seafloor are not like what we often see on land. So this video you're looking at right now is an example. And lava typically oozes out of submarine volcanoes like syrup or toothpaste even, and we think it's actually pretty rare that they actually explode.
All right. Forrest, do we know how many volcanoes are actually in the ocean and where they are?
Oh, that's a great question, Veronique. In fact, much of the seafloor remains unexplored, so we don't know exactly how many volcanoes exist on the seafloor. There are probably millions, most of which are no longer volcanically active. Uh, we do know, however, that most volcanic activity on Earth occurs at tectonic plate boundaries, and tectonic plates are the rigid outermost part of our planet, which moves or drifts over the less rigid interior. And there are three main areas that volcanism occurs. And what Molly was just talking about were the spreading ridges, which are the seams. They look like seams on a baseball that wrap around our planet. And this is where tectonic plates form on the seafloor. The
Those
second,
are the more jagged lines we're seeing on this map. Is that right?
exactly, and they form one enormous volcanic feature. In fact, the largest volcanic feature in our solar system. So that's an exciting place for volcano research. Another site of volcanoes is where tectonic plates are destroyed, or at subduction zones where tectonic plates are dragged deep into Earth. And this is where some of the most explosive and eruptive volcanoes can occur. And
Those are the little triangles
exactly
for
along
the most part, along the coasts more.
along the blue lines,
Yeah.
what we call the Ring of Fire in the Pacific. The third type of location where volcanoes form on Earth is within tectonic plates. And we believe, and Hawaii is an example of this, and we believe that these volcanoes form from magmas that are generated deep in our planet and come through and penetrate the tectonic plates, and they form island chains. So part of what makes studying volcanoes on Earth so exciting is that there's such a diversity of different volcanic features.
Okay, I want to take each one of those in turn and have you talk a little bit more about them. Manuel, I promise we're going to bring you into the conversation, but I'm going to go back to Molly first. You study, as Forrest said, volcanic activity at spreading centers. For the audience, we need to go back and think about when we learned about tectonic plates, but talk a little more about spreading centers. What are they like, and how do volcanoes form there?
Yeah, absolutely. So spreading centers are these globe encircling volcanic chains that look on a map like sutures on the seafloor. So like the map you're looking at here, you see these ridges in the middle of the ocean. That's what these are. And what's happening here is that as the tectonic plates are separating, the layer beneath that plate called the mantle actually rises upward to fill the gap that's forming between the plates. And by moving upward, the mantle experiences lower pressures and it melts. And those melts of the mantle, called magmas, buoyantly rise towards the surface, and they either cool to form the interior of that plate, or they erupt on the seafloor through these rifts. The structure of the ridge is controlled by how quickly these plates are separating, or the temperature of the mantle, or how much magma is actually available below the ridge. So at slow spreading ridges, and this is a good example of that being shown here, there's less magma available and the temperature is generally lower. So the crust behaves more brittly, is what we call it, or it's more breakable when it's stretched. So you can sort of think of this like trying to stretch a graham cracker. It will snap, right? And that happens to the crustal rocks. And it forms these things called faults or fractures between the rocks. And that results in this wide trough shape that you're seeing on this diagram here. By contrast, at the faster spreading ridges, so where the plates are pulling apart much more quickly, there's more magma available underneath. It's higher temperature crust, and so when the crust is pulled, it behaves more elastically, like stretching taffy, for example. So the ridge is also inflated in this setting, so it tends to sit higher than these slow spreading ridges I showed you before, and so it results in this sort of narrow but really elevated summit that you saw.
Mm.
And yeah, so here's some footage actually of the seafloor inside the summit of a fast spreading ridge. And this is from the point of view of the submersible Alvin that we'll talk about a little bit more today. But what you're seeing here are the walls where lavas fill in and then drain out repeatedly. And it leaves behind these structures on the walls that look like bathtub rings, kind of. And the lava flow you're now looking at the bottom erupted most recently in this area sometime between 2005 and 2006.
Oh. I want to go back to that video we saw earlier real quick, what looked like exploding at the bottom of the ocean. So was that a slow spreading center or a fast one?
This is actually part of a very complex back arc basin, so it's a little bit
Sorry, I
different.
asked. Okay.
No, that's okay. This is a much more complicated area. We just got
Okay.
really lucky capturing an eruption here.
Yeah, it's amazing footage. All right, Emmanuel, you study
Hello.
volcanoes that form in a different way at subduction zones. What is a subduction zone, and how do volcanoes form there?
Excellent question. Thank you so much. Yeah, so we've heard from Forrest like what tectonic plates are, and Molly described a special case where the two plates are pulling away from each other. So let's talk about subduction zones. So subduction zones are also plate boundaries, but these are regions where two plates collide, wherein one plate sinks deep into the mantle underneath another plate. So subduction zones are very important because this is where we generate the most explosive volcanic eruptions and the strongest earthquakes. And the gases or the volatiles that are released during an explosive volcanic eruption, as you can see in this picture, can influence the climate and therefore the Earth's habitability.
Yeah, we'll talk more about that later. This is Mount St. Helens, by the way.
Yeah. Oh, yes. So we will talk more about that. And it's also very important because you can think of it as everything that we have on the surface, whether these are rocks found in the ocean floor, sediments, and seawater, are eventually brought back into the Earth's interior at some point in time. And magmatism in subduction zones, as you can see in this cartoon image, is unique in this way because the water that is carried down by the subducting slab could actually lower the melting point of the rock surrounding it, which causing them to melt. And this process would produce magmas that are rich in water. And water, when it dissolves in magma, can actually play an important role in making the eruptions explosive. So water is a key to that explosivity in subduction zones.
Okay, so we've got an interaction there between the ocean and the explosive forces of a volcano.
Absolutely.
Thanks, Emmanuel. Forrest, you sometimes hear about volcanic hotspots. You mentioned the Hawaiian Islands before. So but I'm confused. I understand when you've got plates either spreading or colliding, why that might cause volcanic activity, but how do you get volcanic activity in the middle of a plate where nothing's going on?
Excellent question. And not only is it volcanic activity, it's some of the largest volcanoes on Earth. The Hawaiian Islands are an archipelago of massive volcanoes. From seafloor to summit, they're over 30,000 feet tall, which is greater than the distance from sea level to the top of Mount Everest. So they're just enormous.
Wow.
And these volcanoes form above mantle plumes or parcels of hot rock that drip upward from deep in the earth near the core mantle boundary, we believe. And these mantle plumes are buoyant because they're hot relative to the surrounding mantle. And as they approach the surface, they melt to form massive quantities of magma. And this global simulation is demonstrating how Earth's interior is really dynamic and mixing and stirring. In fact, over geologic time, the ascent of hot rock is cooling the planet. It's much like the convection of water in a tea kettle, for example. The Earth has a lot of heat to give off. Amazingly, about half of this is from Earth's formation. It was a very violent formation involving the collision of different planets to form the Earth-Moon system. And the other half of Earth's heat is from radioactive decay of elements like uranium and thorium and potassium, which exist naturally within Earth. So
wait, I want to go back to that for a second. So half of the heat that's being expelled by volcanoes actually came from when the Earth was formed. Is that what you said?
Half of Earth's entire heat budget is from when Earth formed, and yes, these volcanoes are one of the mechanisms in which the heat is released from Earth's interior. So yes, you could think about it as half of the heat coming out of these volcanoes is actually from Earth's formation 4.5 billion years ago.
Amazing. All right. Molly, so we can see volcanoes like this on land, but how do we find undersea volcanoes that might be kilometers or miles below the ocean's surface in order to map them?
Great question. You know, some volcanoes actually breach the ocean surface, like the Hawaiian Islands, as Forrest was just discussing. And those started beneath the ocean and grew into the largest volcanoes on our planet. But the process forming them is pretty rare. So the ocean forms a sort of barrier for being able to find oceanic volcanoes visually, or even really for developing a global map. 70% of Earth's surface is covered by oceans, and yet only about 25% of that has even been mapped in any detail. On land, we map using aerial and satellite imagery, so we really rely on this like transfer of light to map land. But those technologies don't see through the ocean. And this is why the planet of Mars is mapped in greater detail than our own ocean floor. And so this is where this idea of bathymetry comes in, or our study of the floor of water bodies in the ocean, like our ocean. In the early days, like back in the 1800s, somebody would actually dangle a weighted rope off the side of the ship and measure the water depth by the amount of rope they let out. You know, we've come a long way from
So
that.
until they hit the bottom.
Yeah, and you're hoping that you
Okay.
didn't get caught by a current or something, right? So there's some uncertainty there. But our first complete seafloor map was actually created by this woman, Marie Tharp, and Bruce Heezen, and it was published in 1957. And Marie actually hand plotted this map at a time when women were not allowed at sea. And her map revealed this massive mountain range in the middle of the Atlantic, and it sort of revolutionized the way that scientists really look at how our planet works and plate tectonics operate. So today we map the seafloor using sound with multi-beam sonar, and this is mostly on ships. And what this means is that the ship actually sends and receives sound pulses through the ocean, and it tells us the distance to the seafloor. So this is what a resulting map from that looks like, where the red or the warmer colors represent shallower points, and cool or blue colors represent deeper locations. And in addition to using the shipboard sonar, we also use remotely operated vehicles like this one here called Sentry. and we release it into the ocean, and it actually hovers really close to the seafloor, and it gives us much higher resolution maps. And that becomes really important when we're trying to like find certain features on the seafloor, like a new lava flow, for example. And it really helps us be able to sort of guide where we're going to sample a volcano when we dive.
Really, those images are just amazing.
Isn't that
And
incredible?
I love when we can get into some of the history of oceanography too. It's so
Yeah.
fascinating. Let's go ahead and take our first audience question. My colleague Ken Costell is behind the scenes fielding those as they come in. Ken, what do you have for us?
Oh my, we just got a very long one, but I'm going to stick with ones I have already. I think this might go to Emmanuel. Grant asks, what happens when a lump of the ocean crust, like a seamount in particular, what happens when that is subducted? Is it flattened into the plate or does something else happen?
That's an excellent question. So, it can go in a number of ways, but one common, so if you have seamounts and you bring them and subduct them to deeper depths, as you go deeper, it will experience higher temperature. So sometimes, or more commonly, it will start melting. And yeah, it will melt.
How big is a seamount? Is it like a mountain on land?
They're totally variable.
Yeah,
I
it's
mean,
highly variable. Yeah.
they can be these tiny cones, they can be something
Okay.
significantly bigger than that, but it
Okay.
can cause earthquakes. I mean, we don't fully understand actually all of the dynamics of what happens when you subduct a seamount, but it has to be happening everywhere.
That's true.
Yeah.
And sometimes, depending on the temperature of the slab, it can melt. But if in cases where the slab remains cold, it will bypass and not melt at all. And those subducted seamount can be subducted to deeper depths and then just stay there for millions of years. So
Wow.
their fates are still also very variable, and there's a lot of research that are currently being done to determine their fates.
Ken, let's take one more question before we go on.
Okay. Olivia asks, why is it that oceanic volcanoes seem to ooze rather than explode, and why do land-based volcanoes seem to explode rather than ooze?
That sounds like it's for Molly.
Yeah. That's a great question. And then ultimately a lot of this does come down to the chemistry, which I'll talk to you a little bit more. We'll talk to you all about a little bit more about later. But um it's very complicated what a lava or what a magma actually has to go through when it goes through a continent versus what it goes through when it goes through just oceanic materials. And basically it just comes down to how viscous or how sticky the lava is, really. And in the oceans, these tend to be really loose lavas that just aren't quite as sticky, so it doesn't trap things like gas that would make an eruption explode. But on continents, you're not only do you have this really sticky lava, but that lava is capturing and holding in the gases that are coming from the continents, and so it just builds up pressure and eventually blows.
So just to clarify, sorry, go ahead, Forrest.
I was just saying Molly is exactly right, but a little counterintuitively, the seafloor lavas tend to not have very much water in them. And the subduction zone volcanoes, because seafloors and seawater is dragged deep into earth and then makes it back up to the surface, have more seawater in them, and that makes them more explosive, so, even though they're on land and farther from the oceans.
I was just going to clarify some terms. So it's magma before it when it's still underground, right, or under the seafloor, and then it's lava once it comes out either above into the ocean or on land. Is that right? Okay.
Yeah.
All right. So let's actually get into your research now and tell us a little bit about what you're doing. We'll probably need to define some more terms along the way, but how do you study underwater volcanoes and what are you trying to find out about them? Molly, let's hear about your work first.
Sounds good. So I study the composition of lavas that are erupting from these volcanoes on the seafloor. And I'm a petrologist, which means that I study the processes that form rocks. So I focus on igneous rocks, which are those that form by cooling molten rock or magma. The composition of a lava rock tells us a lot about what melted or how long ago the lava erupted or the conditions that the magma experienced beneath the volcano and even where in Earth that magma came from. And so to do my work, we need to be able to collect rocks from the seafloor. So we use a lot of tools to collect rocks from the seafloor. Sometimes we drag these large metal bags along the seafloor behind the ship, and they're called dredges, or we'll drill into the rocks. But really, if we want to know exactly where a rock came from and the context around it, which is really important in geology for us to understand how something is related to the other rocks around it, then it's important that we use submersible vehicles like the human-occupied vehicle Alvin, shown here. And Alvin has these hydraulically powered arms that we use to collect the rocks while we're on the seafloor. So that's what you're seeing in this photo here. Yeah, it's holding on. You look for something loose that you can pop off of there easily. Yeah, so this is what we like to use. This is like our most ideal tool. And 3 people dive in Alvin at a time. So there's 2 scientists and a pilot. And it's just this absolutely thrilling experience when the pilot seals the hatch above your head and you get lowered into the ocean. And it feels, in a sense, like being an astronaut. Some of us call ourselves aquanauts after we've gone, because you're often going to these places where no human has ever been, and you're not really knowing what you'll find when you get there. So it's pretty thrilling. And finding and collecting and documenting these seafloor volcanic rocks in Alvin has really been the coolest part of my job, I think. But it's really just the beginning of the work I actually do. So when these dives in Alvin are over, there's a lot of work we do at the surface. So we bring the rocks to the ship and we prepare them to bring to labs on shore for analysis. And to understand what these rocks are made of, I cut them extremely thin. I'm talking thinner than a piece of paper, so thin that light will actually pass through them under a microscope. And when we look at a rock this way, we can tell the general composition of the rock and things like if a magma has mixed with something else that can actually lead to an eruption.
So there we're looking at a thin slice of rock that under a microscope.
Yep, this is one of my samples from the seafloor. So it's called a basalt, which is what most of the seafloor is made of. And
how do you slice it that thin?
Oh, very carefully. Well, you cut it with the rock saw first, and then you have to kind of keep cutting it down, and then it gets to a point where you're just grinding it and hoping that you aren't breaking everything, and you have to do it slowly enough but quickly enough.
Wow,
and you just keep grinding it down, polish it down until it's thin enough to see through. Yeah, here's another example. So these are different minerals, and minerals are these building blocks of rocks. And so what minerals we see can tell us a lot about what that rock experienced, what that lava experienced. We can sort of see into the inner workings of a volcano by looking at this type of thing.
Yeah, it really is beautiful when you slice them like that and see all the different colors.
Yeah, and this is just the effect of passing light through them, right? So it just light passes in different ways through different minerals, and we can study them by looking at that.
That's neat.
Yeah. And so another way that we study their composition, and probably the thing I do the most, is actually dissolving these rocks in acid, which is what you're looking at here. And then we take that and we separate out the different components of the solution into, using a process that's called column chemistry. And that's what you're looking at here. And eventually, once we've separated out what we want to measure, then we pump this dissolved sample through a machine like this one called a mass spectrometer. And this machine essentially counts and tells us the composition of the rock.
All right. Emmanuel, you also use some fancy machines, but you take a little bit of a different approach than Molly. So tell us how you study volcanoes.
Yeah, I do. By the way, I just want to say that those are fabulous photos from Molly. In 2017, I was lucky enough to be given the opportunity to also dive in Alvin, and
I
it was
remember.
I think I cried. It was just, I was overwhelmed by, it's just amazing how much we don't know. It's such a different world down there. Yeah, and it's also fascinating to think that, what Molly does is that she collects natural rocks and bring them to the lab and measure the chemical composition. And from their chemical composition, she can get important clues as to how they formed and under what conditions. So, one important point that I want to make is that what we get like this is a lava flow. These are cumulative products of melting and melt transport that occur over a wide range of temperatures and pressure condition. So it is still challenging to determine where they came from and under what conditions were they formed. So that brings me to experimental petrology, which is essentially a subdiscipline of petrology that aims to determine the physical and chemical properties and behavior of rocks and the constituent minerals under controlled laboratory conditions. So what we do as experimental petrologists is we try to recreate the conditions and processes that we think are relevant in the Earth's interior. So, for example, for myself, I essentially make my own rocks at high pressure and temperature conditions. And one analogy that I can give is that in high school, like we were taught like at what temperature water would freeze and at what temperature water would vaporize or evaporate in the simple phase diagrams. So what I do as an experimental petrologist is I also make phase diagrams for rock compositions to determine their melting behavior and like among other properties. So in the lab, so you can see in these photos, there are different kinds of tools that you can use depending on the pressure and temperature conditions that you want to reproduce. So what we see here is a 1 atmosphere gas mixing furnace. It's essentially an oven that can go up to 2000 degrees Celsius under ambient pressure, so room pressure. But that can go up to high temperature, but it cannot reproduce high pressure conditions simulating the interior of the Earth. So if you want to incorporate both or simulate both pressure and temperature condition, we can use other tools such as a piston cylinder device, as you can see in this photo. So these are piston cylinders. These are from—
Sounds like something in your car, a piston cylinder.
Well, they're essentially hydraulic presses. So you have oil that pressurizes, that causes the pressure. So these high pressure vessels, this particular one can go up to 2000 degrees Celsius and up to 4 gigapascals of pressure, or approximately 120 kilometers depth. And what I do is that I make my rocks. I can use synthetic rocks or I can use natural rocks and then put them in teeny tiny capsule or like a pot. And that pot here is represented by that small capsule. Yeah, as you can
Which
see
is made of gold, is that right?
Yeah, so this particular one, so it's gold palladium. So it's a mixture of gold and palladium, and we know the melting point of that particular material. So we put the powder in that teeny tiny capsule, we crimped it shut, and then we put it in an assembly or a pressure assembly, as you can see here. And then this entire crushable component are going to be placed gently into this piston, in this pressure vessel, that big chunk of metal. So this one will be placed into the piston cylinder. And as you can see in this photo, this is done actually by Dr. Emily Sarafian. She's an excellent experimental petrologist. So
and she was also a graduate student at WHOI.
Absolutely. So she actually taught me how to do experiments at WHOI.
Oh, okay. I didn't know that.
Yeah. So now that the entire assembly, including your sample, is within this stack of metals, it will then get heated up and then pressurized for an extended period of time, long enough that the material may have, your experiments have reached chemical equilibrium. And then after the experiment, you take it out, and then you cut them, and then you polish them, and you determine the chemical composition. So Molly collects natural rocks in the field, measure the chemical compositions to determine, to get insights on how they form. One complementary way of understanding how magmas are produced is when you try to recreate melting processes in the lab, and then you're determining the compositions of the magma that you produced in the lab. So that's
Makes
essentially
sense. You're just coming at it from a different angle, kind of.
absolutely. So we are providing a complementary perspective. So this is just a figure showing the depth range if you look at the slice of the Earth. So here I said that the piston cylinder can go down to 4 gigapascals, so which is essentially still very shallow, so upper
Yeah,
mantle.
we're still way up in the upper mantle. Okay.
We're barely, scratching the surface. But if you want to go deeper, so personally, I'm also using another device called a multi-anvil press. So it's similar to piston cylinder press, but a multi-anvil press, which is this big blue chunk of metal, can go up to 2000 degrees Celsius, but at much higher pressure. So this can go down to 20 gigapascals or approximately 600 kilometers depth. So we are now pushing the pressure limits even further. And there are more tools that people use. For example, diamond anvils to reproduce the conditions relevant to the core, but it's something that I don't particularly do. Yeah.
All right. Thanks for that.
Yes. Yeah. So, I cook rocks. I make my own rocks in the lab. I like to cook, and I also like to cook rocks in the lab.
There you go.
The work he does helps us be able to like create models and be able to, understand the things we find at the surface. It's really helpful.
Absolutely.
So, Forrest, you actually study volcanoes on land and the gases they produce. Tell us about that.
Right. Yes. Well, I don't make rocks like Emmanuel or go to the seafloor like Molly, but rocks on land provide a lot of advantages too. We can go up and sample active volcanoes, and this is me scooping out some red hot lava from an active volcano in Iceland, and it's an incredible experience. They're hot, and you feel the heat, and these lavas are crumbling as you're sampling them. So we can sample more selectively and more frequently. We can stay there for a long time, and we can also come back and sample lavas after they've cooled. And I do both of these types of sampling. These volcanic gases in the lavas has been a main focus of my research, and most lavas have a lot of gas in them. And you can see in this image of a lava the cavities or bubbles, which we call vesicles, that formed from the volcanic gases coming out of the lava during the eruption. In fact, the vast majority of the gases come out during eruption, which presents a problem for us trying to study these gases. And our solution to this is to study crystals that formed and grew at depth. And I often study these beautiful green crystals called olivine that form deep in the earth and then carry these gases from these great depths up to the surface. And
so those are like little capsules of gas, basically?
Exactly.
Okay.
I spend a lot of time and energy picking and cleaning these beautiful, almost gemstones, and then I take them into the lab and I crush them to get all of the gas out. But it's completely worth it. We have found one of the exciting findings recently was that we think that helium, magmatic or volcanic helium, captured in these little bubbles or inclusions inside of the olivines has actually come from the very deep earth, from Earth's core perhaps, which is exciting because it challenges the conventional view that Earth's core doesn't leak or exchange anything with the shallower reservoirs.
Interesting.
So these volcanic gases can tell us a lot about the deep earth. And the gases are not only interesting from a scientific perspective, but also from a practical perspective. So I'm working with a team of scientists to explore whether helium in particular might help us forecast dangerous, hazardous volcanic eruptions. We think that the volcanic helium might escape from ascending magma before the magmas erupt and provide a warning signal, essentially. There's still a lot of research we have to do before this is can actually be applied, but it shows a lot of potential.
Fascinating. All right, Ken, we're a little short on time, but let's at least take one audience question right now.
Can we do two short ones? Because I've got a teacher and a student.
Let's do it.
Okay. Cindy is a 7th grade teacher. She asked, because so little of the seafloor is mapped, is it just luck catching an underwater volcano erupting and therefore being able to film it?
I think the answer is kind of yes, but who wants to take that, Emmanuel?
I think there's some luck involved in it as well. But as someone who doesn't do a lot of like ocean floor work,
that's true. This should be for Molly. Molly, what do you think?
Yeah, that's a fair question. It's a really good question. I wish we could just monitor them the same way that we do on land, right? Of all of this equipment left out there and take measurements all the time on what's inflating and what's not and where the earthquakes are, but it's really difficult to actually leave equipment anywhere on the seafloor and be able to get anything in a timely manner. So you have to really predict. And we're trying to do it, but it's very challenging. You have to be in the right place at the right time, and that's hard to do.
The ocean is very large.
Yep.
Yeah.
And then Axel, who is 5 years old, asks, are there active volcanoes on Venus or Mars?
Ooh, good question. I don't know. Who wants that? Molly, do you want to take that one?
Sure, absolutely. Absolutely. I think there's more on Venus, in fact, than, well, yeah, than there is on Earth. And Mars absolutely has huge ones. In fact, Mars has the largest volcano in our solar system called Olympus Mons, and we think it forms similar to how the Hawaiian Islands have formed. So it's very, very large.
All right. I'm going to keep this going just so we don't get so we can get through everything. We have so much to cover, but we've been talking about how you study volcanoes. I want to shift gears a little bit now and talk about why we need to study them. The kind of obvious answer is because they can be dangerous. But Emmanuel, in addition to the immediate danger for people living near an active volcano, what are some of the other hazards that might be associated with them?
That's right. That's an excellent question. I would say, like, for example, underwater volcanic eruptions can displace large amount of water, and that can develop into tsunamis, affecting primarily the coastal communities. Eruptions happening on land often would force people living near the volcanoes to abandon their homes and their lands. So the volcanic ash, volcanic tephras, or rock fragments that are injected during an explosive volcanic eruption can damage crops, can affect transportation systems, that can be both on land and also aviation, that can also affect electric grids. So there's a lot of, it can, the societal impact is just huge. So I
remember that from when the volcano, which I will not attempt to say its name, that erupted in Iceland, there was a lot of disruption from that, I know.
I agree. So I am from the Philippines. And in the Philippines, we have more than 20 active volcanoes and many, many possibly active ones. And maybe some of you in the audience are familiar that in 1991, Mount Pinatubo erupted. And this eruption erupted up to 20 million tons of sulfur dioxide into the atmosphere. And this amount of aerosol was so huge, you can see in this plume, this amount of aerosol during one volcanic eruption was so huge that it resulted to a measurable cooling of the Earth's surface for almost 2 years. And I want to emphasize here that, this single event from a tiny piece of land at one point in time impacted the entire world, the global temperature for several years. So it just, it's just fascinating to think how volcanoes and volcanic processes affect us, both in direct or direct ways.
So the blue we're seeing on this map is the actual cloud cover. Well, that's not clouds,
Yes,
but from
like
the volcano.
yes.
Wow. Forrest, how else has volcanism shaped our planet?
Oh, well, it's really difficult to exaggerate the role of volcanism on planet Earth. The crust is primarily formed via volcanism, and volcanism contributes to why we have such a geologically dynamic planet. This is an ocean world we live on with these vast oceans that are really intimately linked with volcanism. Seawater, like Emmanuel was talking about, dragged to great depths in the planet, is then triggering melting, which causes volcanism. On the other hand, these volcanoes are delivering water back to the surface, replenishing the oceans. And so the oceans are sustaining volcanism on our planet, and the volcanism is sustaining oceans on our planet. Even our continents really owe their existence to volcanism, because this seawater volcano interaction has created magmas that are less dense than those that form the seafloor. And over eons, these have accumulated to form the continental crust, which is now less dense and floats higher and is therefore above sea level. So, we have volcanoes to thank for the planet we live on in a lot of ways.
Yeah. So we've been talking a lot about geology and geochemistry tonight, but where does biology fit into all of this? Molly, how do underwater volcanoes affect life on the seafloor? Are they good? Are they bad?
It's a great question. Most of the seafloor is fairly devoid of life due to the lack of available food. But in these volcanic regions, there's these hot springs that form called hydrothermal vents. And that's what this schematic here is showing you. And these vents provide really important chemicals that allow bacteria and microbes to form food in a process that we call chemosynthesis. And the reason that these hydrothermal vents form is intimately tied to magma bodies in the crust. So seawater is percolating through the cracks in the seafloor toward the magma bodies, which superheat the fluids, and the chemicals from that crust are actually transferred back up to the surface. And they precipitate out, they form these beautiful chimney structures where all of these creatures thrive. And bacteria are using the chemicals coming from these vents, like carbon dioxide and hydrogen sulfide and oxygen. And this forms the base of the food chain at a vent. And so you see things like the shrimp shown here, or mussels, zooplankton, or tube worms, I think was maybe the last
Yeah, we
video.
saw some tube worms.
Yeah, with the white tubes and the red plumes sticking out. Those are sort of classic hydrothermal vent creatures, and all of these use that bacteria. And then you go further along the chain and there's crabs and there's fish, like the zooarctic fish, and you'll hopefully see that soon. It's like a pale pink fish, and those feed off of the zooplankton and the worms, and then in turn the octopus eat the crabs and so on. So it's really a delicate system where without these magma bodies, this food chain in an otherwise really cold, dark, deep sea environment really wouldn't function.
Some folks in our audience may remember hydrothermal vents. We had an Ocean Encounters all about them, and I encourage you to go to our website actually and look that one up. That was a great event as well. So, and we'll have some more. I meant to say this earlier in the program, but we have some great footage, brand new footage of hydrothermal vents that we're going to share with you at the very end of our program. So please stay with us for that. But first, let's go ahead and take some more audience questions. Ken?
I missed the person who asked this, but I think a couple people asked, are there volcanoes in the Arctic and the Antarctic?
I don't know, Forrest?
That's a great question. There are, in fact, there's a spreading submarine spreading ridge in the Arctic. course, the North Pole is in ocean crust. And there are active volcanoes in Antarctica. I've had the pleasure of seeing some of those. And they're actually, one of them is my background right now, Mount Discovery.
Ah.
This actually is not an active volcano at the moment, but a nearby one called Mount Erebus is very active. So yes, volcanism occurs at the poles.
Great. Ken, we can take a couple more.
Ginger is watching us on YouTube, and she was asking, what's the most interesting volcano each of you have seen in the ocean? But I guess we have to expand that to on land for Forrest.
All right, so let's start with Molly.
Oh, hard question. In the
What's your favorite
ocean,
volcano?
yeah, my favorite volcano. Goodness, that one's a stumper. I think
All
the
right.
ridge itself, it's this incredibly long volcano. You could argue that it's one volcano, really, but I mean, kind of not because there's so many magma bodies underneath. But it's, I don't know, it's such a strange and unique feature that I don't know, I find it absolutely baffling the type of magmatism we get there and the life that exists at these ridges and just how pervasive they are. They're huge, right? Like we don't even know they're there until you look at these maps. So I'd say that's probably the most interesting for me for for a submarine volcano.
Emmanuel, do you have a favorite volcano?
Well, I think I do. Well, even though I study mostly subduction zone volcanoes, I would say that my favorite one would be the time when I dove in Alvin. So we went to the ridge axis in the middle of the Mid-Atlantic Ridge. So it's essentially where two plates are pulling apart, so it's a spreading center. So that's essentially where new rocks or new oceanic crust are formed. So you're looking at basalt of zero age. So just being there where the two plates are pulling apart, I was there. And it was just fascinating. And I think it's hard to tap that as an experience for myself. So yeah, I would say that.
All right, and Forrest.
Well, I have to say, well, I'm going to broaden the question to on land too, but my favorite volcano, or the one that fascinates me most, is probably Oldoño Lengai in Tanzania, which is a very, very odd volcano because it's made mostly of carbon minerals rather than silicon minerals, which we normally see. And it's a scientific mystery to a large extent. So I'd love to go there sometime and see it for myself.
All
The
right.
I'll join
lava's
you.
colored weirdly there too. I mean, isn't it completely weird? It like flows out like water, and I mean, it's a weird
Exactly.
volcano.
Yeah. Yeah, and the lavas change color almost overnight. They come out dark and then turn light because there are so many chemical reactions. It's just a
Wow.
very odd place.
Oh, I'd love to see
So,
that too.
so Forrest, let us know when you decide to go there. We'll definitely consider joining.
You're sure welcome.
There
It's
you
a
go.
plan. Yeah.
All right. Ken, do you have one more question or?
Sure. I've got a lot more. Ted asks, so when lava erupts, it creates a void below it. Where does the material come from to backfill that? Or does it even create a void?
So I can jump in and feel free to jump in as well, guys. So for example, if you have a very explosive volcanic eruption, meaning that you are spewing a lot of materials from the magma chamber, pushing it out to the surface. So that will definitely make a void in where it was stored originally. So that can cause collapse. Like a caldera collapse. So that will cause and form like deep like depressions that we call caldera. Yeah.
All right. We
Just
are
quickly, Forrest,
yeah.
somebody is asking how you spell the volcano you mentioned.
Oh, it's Oldoño Lengai.
Okay, I can put it in the chat.
Yeah, why don't you put it like
Oh,
it's
Got it.
yeah.
I am.
Okay.
Never remember whether
We'll
it's two
put that in the
words or
chat.
one.
So,
Yeah.
all right. So we're getting close to the end of our time here, but I'd like to ask each of you one more question very briefly. What got you hooked on studying volcanoes or geology in general? Let's have Forrest, then Molly, then Emmanuel.
Well, I've always loved the mountains and been drawn to them. I think in terms of volcanoes, I'll never forget my experience climbing Mount Shasta in Northern California. It's just this majestic snow-capped volcano rising out of the plains. And I remember getting to the summit and smelling volcanic gases and just being blown away by with awe and wonder at this very powerful, enormous process going on beneath me that largely don't see because it happens on different time scales. Yeah.
Molly?
For me, it also goes back to honestly having grown up. I grew up in an area completely surrounded by lava rocks in Idaho, in the footprint of the Yellowstone supervolcano, without even knowing what had formed this like really dramatic landscape around me. And then in college, my volcanology professor brought our class to Mount St. Helens, and I learned that we can forensically determine what happened during one of the most destructive eruptions in our country's history by looking at the chemistry of a rock. And from there, I was completely hooked on understanding how volcanoes work.
All right, and Emmanuel, you get the last word.
Oh, yeah. So I also want to highlight how mining or economic deposits can be linked to magmatism. So we have to thank, melting on Earth in making this economic deposits, because that's one way, an efficient way of extracting metals from the Earth's interior to the surface to the point that we can economically extract them. So coming from the Philippines, we have a lot of economic ore deposits in the Philippines. And so back then, there was an expectation for me to go to mining as a potential career. But I later realized that, while you're looking at rocks, there's a lot of information you can get on these rocks, not necessarily on metals, but on how the Earth is formed. So I found that you can look at rocks and then also make your own rocks in the lab.
So science won out. I like that. That's a good way to end. Unfortunately, that's all we have time for tonight. I want to say a big thank you to Emmanuel Codillo, Molly Anderson, and Forrest Horton for joining us to talk about volcanoes. Thank you also to all my WHOI colleagues who have been working very hard behind the scenes to make this event possible. And to everyone who joined us on Zoom, Facebook, and YouTube, thank you. Tonight's event was the second episode of our 6th season of WHOI's Ocean Encounters events. Our next Ocean Encounters is scheduled for April 24th, and that will be about sea level rise, so tune in for that. You can watch our website, whoi.edu, for more details. In the meantime, you might want to also take a look at the very cool merchandise on WHOI's online store. That's shop.whoi.edu. You get a 15% event discount for joining us tonight. Just type in the discount code Volcanoes. And that's with an E, by the way. Volcanoes with an E. There we go. If you enjoyed tonight's Ocean Encounters program, you can be part of WHOI's solution-based approach to ocean science. If you're already a WHOI member, thank you very much. If not, please consider joining. You'll be providing crucial support for our outreach and our science, and you'll get some great benefits in return. Memberships start at just $40 a year. The average gift is $120, but any amount helps. Your support will make a difference. If you have a few more minutes, please stay with us. We have some exciting brand new footage to share with you from the bottom of the ocean, literally just from last week, I think, where researchers have just discovered 5 new hydrothermal vents on the seafloor of the Eastern Pacific Ocean. A collaborative team from WHOI, Lehigh University, Scripps, and others participated in the expedition. Also on the cruise were the deep sea robot Sentry, the yellow robot you saw earlier, and the human-occupied submersible Alvin. Their remarkable technical capabilities and, of course, the expertise of the people on board led to the vent discovery and to the amazing footage you're about to see. On behalf of Woods Hole Oceanographic Institution, thank you and good night.